On a digital computer, all information is represented as sequences of ones and zeros. This is because it's relatively easy to design circuits that switch on and off, and so we can use on to represent 1 and off to represent 0. And so this means that before we can study the circuitry inside a computer, we need to first understand how we can use sequences of zeros and ones to represent data. We'll start with numerical data types, and in particular, integers in base 2, otherwise known as binary. The ordinary number system that we're used to operates in base 10, where a number is represented by digits between 0 and 9, and where each position in the number corresponds to a particular power of 10. So the number 5,845 is made up of 4 digits that each represent a multiple of a different power of 10. On the right, we have the ones column. Then we have the tens column, then the hundreds column, and then the thousands column. And so as we move from right to left, each column represents the next larger power of 10. We have the number of ones, which is 10 to the 0. Then we have tens, 10 to the 1. Then we have hundreds, 10 squared, and then we have a number of thousands, 10 to the 3rd. And so we can write an expression for the number that we mean when we write 5,845 in terms of these powers of 10. We have 5 times 10 to the 3rd, plus 8 times 10 squared, plus 4 times 10 to the 1st, plus 5 times 10 to the 0. It certainly must seem tedious to write this all out for base 10 that we're all familiar with, but by describing it in this way, we can much more easily think about the possibility of using some power other than 10 as the basis for our number system. So by analogy to our familiar base 10 number system, when we talk about base 2, we have digits from 0 up to n minus 1. So we have the digits 0 and 1. And then each position in a number represents a power of 2. And so if we write down a number in binary, we can think about the value of every column in much the same way we do in base 10. So for this number in binary, we start with a column for 2 to the power 0. After our ones column, we have a twos column. After our twos column, we have a fours column. Then an eights column. Then a 16s column. Then 32, 64, and 128. And so for a number in binary, we can understand what value it expresses by adding up the value represented by each of its columns in the same way that we did for decimal. So if I give you a number represented in binary, you can convert that to a number represented in decimal. But what if I gave you a number in base 10 and asked you to convert it to base 2? Well, there are a couple of possible approaches. What I will call the top-down approach to converting from base 10 to base 2 starts by finding the largest binary digit and then working towards smaller columns. And the idea is that we will start by finding the largest power of 2 that's smaller than the number we're trying to convert, and put a 1 in that position. Then we'll subtract that power of 2 from the number and repeat with the remainder until the amount we have left is 0. This will make a lot more sense if we try it on an example. If we want to represent 314 in binary and do the conversion using the top-down approach, we start by finding the largest power of 2 that's smaller than 314. So we can start doubling 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. So 256 is the largest power of 2 that's less than 314. 256 is 2 to the 8th, so we'll need digits for 2 to the 8th down to 2 to the 0, and so we'll need at least 9 bits to represent 314 in binary. So we just determined that 256 is the largest power of 2 less than 314. So now we put a 1 in that position. And then we want to subtract the power of 2. So we subtract 256 from 314. And we get 58. We haven't reached 0, so we'll keep going. The next powers of 2 smaller than 2 to the 8th are 128 and 64. Those are both larger than our remainder. And so the next power of 2 that's smaller than 58 is 2 to the 5th, or 32. So we'll put a 1 in the position for 2 to the 5th, and we'll put zeros in the positions that we skipped. And now that we have a 32 in our binary representation, we should subtract off 32 from our remainder. "26 is larger than the next power of 2, which is 16. So we put a 1 in the 2 to the 4th position. And now we subtract off 16. The next power of 2 is 8, which fits, so we put a 1 and subtract it. Four doesn't fit, but 2 does, and when we subtract 2, we'll get a remainder of 0, and we'll be done. And so now we have a 9-digit base 2 representation of the integer 314. And it's common to write binary numbers with the prefix 0b to indicate that they're in binary. And so its value would be this. An alternate approach is to work bottom up, so starting from the smallest binary digit and working our way to the left. The bottom-up approach operates on the principle that an odd number ends with a 1 in binary and an even number ends with a 0 in binary. And much like in base 10, we could throw away the last digit by dividing by 10 and ditching the remainder. We could, in base 2, throw away the last digit by dividing by 2. Again, let's see this in action operating on the number 314. This value is even. So in the rightmost position, we'll put a 0. And then we'll divide by 2 and throw away the remainder. $157 is odd, so we'll put a 1 in the next position, and then we'll divide by 2, giving us 78 with a remainder that we throw away. 78 is even, so we put a 0, we divide by 2, we get 39. 39 is odd, so we put a 1, we divide by 2, we get 19. 19 is odd, so we put a 1, we divide by 2, we get 9. 9 is odd, we put a 1, we divide by 2, we get 4. 4 is even, so we put a 0. We divide by 2, we get a 2, which is even, so we put a 0. We divide by 2, we get a 1. 1 is odd, so we put a 1. We divide by 2, we get 0, and now we're done. And so our 314 in base 10 is equal to this value in base 2, which is luckily the same value that we got by the top-down method. Base 2 is quite special to computers, but mathematically there's nothing special about 2 or 10 as a base. We could use any integer greater than 1 as the base for our number system. And in particular, it's worth talking a little bit about base 16. Base 16 is particularly useful to computer scientists because 16 is a power of 2, which makes conversions between hex and binary particularly easy. But to represent things in base 16, we need more than the 10 standard digits. And so we start using letters from A through F to help us represent the single-digit values 10 through 15. So in base 16, we have digits corresponding to 0 through 15, and we use letters to represent the digits that our standard Arabic numerals don't have an option for. If we consider the hexadecimal number 2AE, then the E is in the ones place, the A is in the 16s place, and the 2 is in the 256's place. And so 2AE base 16 is equivalent to 2 times 256 plus 10 times 16 plus 14 times 1. And so in base 10, that gives us 686. If we want to convert a number in base 10 to a number in base 16, then we can use a top-down or bottom-up approach similar to how we converted to base 2. For the top-down approach, we will again find the largest power of our base that fits within the number. But now we have to consider how many times does it fit, because the number we put in that column need not be just 0 or 1. If we count up in powers of 16, we have 1, 16, 256, 4,096, and then 65,000 something. So the largest power of 16, that's less than 5,845, is 16 cubed, or 4096. Since 4096 is 16 to the third, we know we'll need columns for 16 cubed down to 16 to the 0. And so the value that we put in the 16 cubed column is the number of times that 4096 goes into 512, which is just 1. So now we subtract, and we get 1,749. Up next is the 256's column, and 256 does fit. And so now we need to figure out what is the largest multiple of 256 that is less than 1749. So we divide this by 16, and we get 6 remainder 213. And so 6 256's fit in our remainder, so we put a 6 in the 16 squared column. And now we see how many times 16 fits into our remainder. This should have been 16 squared. When we divide 213 by 16, we get 13 remainder 5. 13, using our hex digits, is a D, so we put D in that position. And now, how many times does 16 to the 0 go in here? The answer is 5. And so now we have a hexadecimal representation of 5,845. We could also work bottom up, and again, it's similar to what we did in binary, only in binary we were just checking whether the result was even or odd, which is comparable to taking the value mod 2. Now we will take the result mod 16, and we will fill in to the rightmost digit the value of our remainder mod 16, and then we'll divide by 16 to throw away that last digit. So if we compute 5,845 mod 16, we'll get a 5, and then we divide by 16 and throw away the remainder, which gives us 365. 365 mod 16 gives us 13. So we would fill in a D. and then we divide by 16, which gives us 22. Then we mod 16, which gives us 6. Fill that in, and then we divide by 16, which gives us 1. And finally, we mod 16, which gives us 1, and we divide by 16, which gives us 0. We fill in the 1, and we're done. And so we get the same result, constructing from right to left. So why have I introduced hexadecimal? Well, the answer is not because it's fun to convert between base 10 and base 16. It's actually because base 16 makes working in binary much more convenient some of the time. In particular, since 16 is 2 to the 4th, there's a direct correspondence between groups of 4 digits in binary and a single digit in hex. And so it's often convenient when we're working with large numbers in binary, rather than trying to read a string of 32 or 64 ones and zeros, to group up the digits of the binary number 4 at a time, and instead read them as hexadecimal digits. If I ever ask you to convert a number in decimal to both binary and hex, you shouldn't do both of those conversions starting from decimal. Your life will be much easier if you first convert from decimal to one of binary or hex, and then convert directly between binary and hex, which is a much, much simpler task. To convert a number in hex to binary, take each digit individually and convert that digit to 4 binary digits, and the result will be the entire number expressed in binary. So 1 in base 16 is 4 digits 0001 in base 2. 6 in base 16 is no 1s, a 2, a 4, and no 8s in base 2. D in base 16, which we know is 13. For 13, we want an 8, we want a 4, and we want a 1. And for 5, we get no 8s, a 4, no 2s, and a 1. And so this number, represented in binary, is just the concatenation of the binary representations of its digits. And we also see that when we're representing large numbers in binary, this can get quite hard to read, and so it's often useful to group up our binary digits and convert them into a hex digit to have something that we know is closely tied to binary, but is much, much easier to read. One more concept about other bases that will come in handy, especially in base 2, is that it's really easy to multiply by a power of the base. If we have a number like 199 in decimal, and we want to multiply it by 10, we can just add a 0 to the end, which is equivalent to shifting all of our digits 1 to the left, and then filling in a 0 in the ones column. If we want to divide a number by 10, and we're doing integer division where we throw away the remainder, we can do that by just throwing out the last digit, or equivalently, shifting all of the digits 1 to the right and throwing away anything that goes past the decimal point. In base 2, these same operations, shifting everything 1 to the left or 1 to the right, multiplies by 2 or divides by 2. If I have my base 2 representation of 199 from before, and we want to multiply this by 2, we can do that by shifting all of our digits 1 to the left and filling in a 0 on the right-hand side. So this is the binary representation of 199, and this is the binary representation of 398. Similarly, if we were to shift everything 1 digit to the right and throw away the remainder, then we would be dividing by 2 with integer division, and so this gives us 99. And we could verify that by checking that we have 64 plus 32, so 96 plus 2 plus 1 gives us 99. Likewise, in base 16, we could shift to the left and put a 0 on the end to multiply by 16, or we could shift to the right and throw out the last digit in order to divide by 16. So now we know how to represent integers in base 2. But there's a problem, which is that every number that I've shown you so far has been a positive integer.